Fuck.
Hello, everyone. Hope you're all doing well. Do a quick look at the syllabus here. So make sure you know the test that's going to be this Sunday, Monday. I'll remind you guys on Monday. It will be over your organic stuff, so chapter 11 and 12. 11 being all the alkanes, alkenes, alkynes, and then chapter 12 being alcohols, thiols, ethers, aldehydes, and ketones. We're almost done with chapter 12. Just got a little bit left. So we're actually gonna today start lecturing forward on some things with carbohydrates. Carbohydrates will not be on this test on Sunday though. Okay, so let's finish off talking about just some of the different reactions. We've gone into dehydration of alcohols. So it doesn't matter how long the alcohol chain is, right? When this undergoes dehydration, the OH or the alcohol group on the carbon is going to attach with an adjacent hydrogen from an adjacent carbon, create water. That's the dehydrating quality of it. And then if this carbon loses this and this carbon loses this, then they need to fill in because they all want to have 4 bonds or 4 connections. So they will fold that in to make a double bond or an alkene. As far as oxidation and reduction go, remember oxidation reactions increase the number of carbon-oxygen bonds. So any way that we can increase that carbon-oxygen connection or lose hydrogen is oxidation. Reduction is the opposite. So we're going to reduce the number of carbon-oxygen bonds or add hydrogen. So if we look here, we've got no oxygen bonds. This is an alkane. If I was to undergo the first oxidation, it would bring it to an alcohol. So here's our alcohol. Now we have one of our carbons bonded to an oxygen and it has a hydrogen buddy. It follows a pretty consistent pattern, okay? So alkanes will oxidize to alcohols, specifically primary alcohols. Primary alcohols will move to aldehydes and aldehydes to carboxylic acids. Let's talk about this step right here. So oxidation of a primary alcohol. Remember, a primary alcohol is when your OH group is connected to a carbon that has only one carbon buddy. So do you see here, this carbon has 2 hydrogens that it can like lose or detach and just 2 hydrogens and then just 1 carbon buddy. So that gives it the primary quality. This OH is also at the end of the chain. So what can happen under oxidation is if we want to go from a primary alcohol to its oxidized state, we want to increase the number of oxygen carbon bonds. So right now I have a carbon and it's bonded to 1 oxygen. Well, if I can make this a double bond, that will then increase my connection between carbon and oxygen. If I double bond this, what happens is now carbon has 1, 2, well, if I put the double bond in, it would be 2 here, 3, 4, 5, too many bonds. So one of these hydrogens has to go away. And if this oxygen is creating a double bond, this hydrogen also has to go away. So we say goodbye to this hydrogen, we say goodbye to one of these hydrogens, and we get this new structure. Here we've got our carbon, it's double bonded to an oxygen and it has 1 hydrogen. Well, what is that? That's an aldehyde. There's our carbonyl group, al at the end. When we have the carbonyl group at the end, aldehyde. So primary alcohols will always oxidize to aldehydes. Doesn't matter again how long this chain is. If this chain was 16 carbons, it would still oxidize to an aldehyde because the important stuff is happening at the end. What if we look at a, if we wanted to oxidize even further, so we take our aldehyde, which is right here, and I want to increase my carbon-oxygen bonding. Well, I can't put a triple bond here, that doesn't work. But what I could do is I could shove an oxygen in here. So it would be carbon double bonded to an oxygen and then bonded to an oxygen, hydrogen, or an alcohol group. And what happens is the aldehyde will then oxidize to our carboxylic acid, that COO group, COOH at the end. Here we have 3 bonds, 1, 2, 3. Here we only had 2. What about if we want to oxidize a secondary alcohol? Remember, a secondary alcohol is when we have an OH group somewhere in the middle of the chain. So this carbon, we take our OH, we go back to the carbon, and we see how many carbons it's bonded to. It's bonded to 1, 2. 2 carbons, secondary. This carbon, though, does still have a free hydrogen. So what will happen here is if we oxidize this, we're going to increase the connection between carbon and oxygen. So instead of a single bond here, I'm going to make it a double bond. If I make this a double bond, that hydrogen falls off, and then this hydrogen here will also have to fall off. Why? Because if I have a double bond here, I can't have 5 total bonds. Well, this isn't going to break, and this isn't going to break. It's going to be the hydrogen that breaks. So if the OH is in the middle and we oxidize this thing to create a double bond, well, what happens when your carbonyl group is in the center? It becomes a ketone. Again, doesn't matter how long this chain is or this chain is. So primary alcohols oxidize to aldehydes. Secondary alcohols oxidize to ketones. Right, the alcohol is in the center, the ketone group is in the center. If we go back, the alcohol is at the end, it oxidizes, and our carbonyl group is at the end as well, or our aldehyde group is at the end. What about a tertiary alcohol? So here's a tertiary alcohol. I have my OH. I go to its carbon, and I see how many carbons it's bonded to. 1, 2, 3. This carbon here has no hydrogens to play around with. It has 3 linked carbons. These bonds are very, very strong. So there's no H to oxidize here. So if I was to try and shove another bond here to increase my carbon-oxygen bonding, I would have 1, 2, 3, 4, 5 with nothing to give up. Carbon's not going to have 5 bonds like that. So there is no oxidation of a tertiary alcohol. It just won't happen. Excuse me in my full winter garb. I'm like freezing while I'm drinking a smoothie. I don't know why I was craving a smoothie, but I am when I'm freezing cold. So that is why I'm totally decked out. Okay. So know how the different alcohols oxidize. Methanol poisoning, we'll leave that. You don't need to worry about oxidation of thiols. Okay, don't worry about that. Here's ethanol. Ethanol, which is an alcohol, acts as a depressant and kills or destabilizes more people than any other drug. Consumption can be analyzed by using what's called a breathalyzer. It's metabolized by a social drinker at a specific rate of 12 to 15 milligrams per deciliter per hour. If you consume more than this per hour, that's when you get drunk, right? You have too much alcohol. So here is a system where we have our ethanol or our ethyl alcohol. Our body will oxidize it into acetaldehyde, and then it can get oxidized further to CO2 and H2O. But the important thing being here, see the Alcohol, the OH is at the end of the alcohol, so it will oxidize to an aldehyde, al at the end. Effects of alcohol on the body. Okay, yeah, so here's it's slightly dizzy, talkative, euphoria, loud talking, right? Unconsciousness is down at like 12, and coma and death. Don't drink more than, I'd say stay the happy place right here, 2 to 4 drinks. That's the good place. That's where we all try and maintain it, right? Doesn't always work out, but. We're not going to talk about Toland's test. So don't worry about Toland's test. Don't worry about Benedict's test. I'm not going to quiz you on those. Yeah, don't worry about this. Let's talk about reduction of aldehydes and ketones. So if you're going to reduce, that means you're going to increase hydrogen and you're going to decrease oxygen bonds. So if I have an aldehyde, it's sort of the reverse of what we just talked about. If I have an aldehyde, which is this thing right here, and I'm going to reduce it, that means I'm going to add hydrogen back into it. Well, I'm going to then move into a primary alcohol. All right, just like if I take a primary alcohol and I oxidize it, I become an aldehyde. Well, if I take an aldehyde and I reduce it, I become a primary alcohol. Same situation with ketones, right? If I have a ketone and I add hydrogen to it or I reduce it, I'm going to become a secondary alcohol. Just like if I'm a secondary alcohol and I oxidize, I'm going to become a ketone. So those two things are interchangeable. So let's look at this here. I want you to take this thing and I want you to oxidize it. And then figure out what its formula would be, or its condensed structural formula. So remember, when you oxidize, you want to increase the number of carbon-oxygen bonds, but then also take into account hydrogen changes and things like that. Okay, so a couple ways you can go about this. One way is just to conceptually look at this and see, oh, this is an alcohol. This is an alcohol. And it's specifically a secondary alcohol, okay? Because this carbon has a group here and a group here, so that makes it secondary. Anytime you have a secondary alcohol, this is always going to oxidize to what? To a ketone. So I could just find where the ketone is. All right, this is the ketone here. Other thing you can do is like draw it out. Well, the only place where there's carbon-oxygen bonding happening is right here. I want to increase this. So if I increase this, I'm going to double bond my carbon-oxygen, but that's going to pack too many bonds for the carbon and for the oxygen. So I've got to ditch this and I've got to ditch this. And then it becomes this. So B is the correct answer. All right. We have this thing. Select the product when you have propanol undergoes each of the following reactions. So this slide is giving me a headache. Okay, so I don't know why these things are over here. That's a little confusing, but so it's wanting you to go through the oxidation process twice. So we have this thing here. We're going to oxidize once, and then we're going to oxidize twice. So the first time we oxidize when looking at this structure, I want to increase the number of carbon oxygen bonds. So I can make a double bond here. But if I make a double bond there, I've got to get rid of one of these H's and I've got to get rid of one of these H's. So your first B is going to be this here. We have carbon double bonded to an oxygen and then single bonded to one of the other hydrogens. If I take this thing and I oxidize it once, well, I need to increase the number of oxygen bonds. I can't do it here. So what I'm going to do is shove an oxygen in right here, or 4 will be our next oxidation. So it goes from your alcohol to your aldehyde, and then your aldehyde to your carbonic or carboxylic acid group. Again, don't get worried about the rest of the chain. I mean, if this chain was 15 carbons long, the important thing is just what's happening at the end. So we go from this, we double bond first, then we shove an oxygen in to make an alcohol in there. Okay, given the primary, give the primary product for the reaction of 2-propanol when it undergoes oxidation and dehydration. I want you to do this one. So take 2-propanol. First thing you got to do is draw the structure for 2-propanol. Then I want you to oxidize it. And then I also want you to dehydrate it. So each of those will take you a minute or two. So I'll give you 5 minutes to work through that. First, draw the structure, oxidize it, and dehydrate it. When you're oxidizing, you're increasing carbon-oxygen bonds. When you're dehydrating, you're going to try and strip the water away. Okay, let's take a look at this. I'm gonna draw it over here. Okay, so we have 2-propanol. So prop, right, 3. All meaning there's an alcohol on the second. You know what, I'm just gonna draw all my H's out expanded so it's a little easier to see what's going on. So the first thing that we're gonna do is we're gonna oxidize this. If I oxidize it, I want to increase my bonds. So where is the increased bonding going to happen? Right here between the carbon oxygen. If I throw another bond there, though, I have to ditch these 2 hydrogens. So my product will be CH3, C double bonded to an O. It loses the only hydrogen it had, double bonded to CH3, plus 2 hydrogens. It gave off the hydrogens. Questions on that? Remember, a secondary alcohol will oxidize to a ketone. So this is oxidation. Let's look at dehydration. So I've got C, H, H, H. I'll just expand them all so that we can get an idea of what we're doing. Okay, in dehydration, we're gonna take away, remove water. So I'm gonna take this and then one of the hydrogens from an adjacent carbon. I'm just gonna pick this one. These guys are gonna pop off and form an H2O. And usually this happens like with like a platinum catalyst or something. So I have water, and then I have the remaining structure. Well, what happens if these bonds are no longer have buddies? They have to fold, They have to fold in here to make a double bond. So plus, and I'm gonna condense this, CH3 bonded to CH double bonded to another CH3. So here we will now increase to a double bond, or this is an alkene. So in the process of dehydration, alcohols will dehydrate to alkenes. So you want to be able to do those or understand them. Right, I'm not grading things by hand in the sense that you're not writing out your answers. So if it was a real test, I'd probably like literally give you a word problem like this and you'd have to write it out. You'll pick multiple choice style. So at least have enough knowledge that you know that what they're gonna reduce, dehydrate, and oxidize to. Okay. There we go. Go with that. We're not worrying about toluenes right now. Okay, so that's the end of our functional group chapter for organics. So that will cover everything that's on your next test. So just make sure chapter, I believe this is 11 and 12, you are good to go with on Sunday, Monday. We are going to lecture ahead though, so I don't want to cram us too much into next week. So let's get started in carbohydrates. We will kind of work on the carbohydrate lab together, probably next week. Today we'll just discuss it. Okay, so in this picture, we've got Paula. She's a diabetic nurse, and she's teaching this woman, Kate, how to test her blood for glucose levels before and after a meal. So glucose is a type of carbohydrate that we find in our bloodstream. We need it for energy. Depending on how your body regulates glucose with insulin, you can have issues where you're hyper or hypoglycemic, you have diabetes. So what is a carbohydrate? All these things over here are carbohydrates. Carbohydrates are super yummy, especially when you combine them with dairy. They're a major source of energy of our diet. What defines them as a carbohydrate is that they contain carbon, hydrogen, and oxygen. Okay, so whereas a hydrocarbon, our simple hydrocarbons, those were just carbon and hydrogen. These are carbon, hydrogen, and oxygen. Another name for a carbohydrate is a saccharide, which means sugar. So carbohydrates are sugar. And so when you look at all this stuff over here, it's not quite as bad as a pile of candy, but it's not much better. This one has some nutrients in it, but these guys here, yeah, not much better because your body just digests them as sugar. So one example of a carbohydrate is glucose. Here's glucose over here. It's C6H12O6. How does this form? Well, plants can produce their own glucose through a process called photosynthesis. So what they'll do is they'll pull CO2 out of the air, which is something that we exhale, so it's good. So the plants use our byproduct, and then we use oxygen, which is their byproduct. That's why we need them around. So it'll take CO2 out of the air. It needs a source of water, and then it needs energy. And the energy that it's receiving is from the sun. And under the process of photosynthesis, the CO2 and H2O end up being oxidized to produce glucose and oxygen. Now, the reverse also happens here in what's called respiration. That's what we do. So we breathe out. So we use glucose, we breathe in oxygen. That process allows our body to receive energy. And then when we exhale, we will exhale CO2, H2O. So different types of carbohydrates. This is sort of the simplest way of organizing them. We have monosaccharides, which are the simplest types of carbohydrates or sugars. So here's a picture of a monosaccharide. And you will see these carbohydrates sometimes drawn as rings like this, or sometimes they're drawn like this, uncoiled. So just be comfortable that like these long things can coil up, and it's the, excuse me, it's these rings here. Okay. So a monosaccharide, because it's the simplest carbohydrate, if I put it in water and I add like some sort of enzyme or put it in like an acidic solution, it's not going to hydrolyze, meaning it can't break apart into a simpler thing in that way. You'd have to undergo something else to break it apart. A disaccharide is something that contains two monosaccharides chained together, and there's a couple different ways that we can chain them, and we'll talk about those. But here we've got one monosaccharide ring and another monosaccharide ring, and they're connected together by this oxygen ketone bond here. Well, if I put this thing in water and then I add some sort of enzyme, I can break it apart into simpler monosaccharides. You get two monosaccharides for every disaccharide. Then we've got these things called polysaccharides or complex carbohydrates, which contain a lot of simpler monosaccharides chained together. A polysaccharide we would have to add a lot of water, but we can use water with an enzyme and we can break it up into many monosaccharides. So have you ever heard of like simple carbohydrates and complex carbohydrates? Simple carbohydrates are things that have just single monosaccharides. Those are really, really easy for your body to digest. So if you eat a lot of simple sugars, like table sugar and honey and things like that, your body is really efficient at just using that or storing it as fat. If you have a complex carbohydrate, your body actually has to use energy to break it down into the simpler form. So you burn calories in order to get the calories out of this. So that's why, you know, things that are complex carbohydrates like quinoa, healthier than say something that's like super, super simple. So rewind, these aren't quite as equivalent to a thing of candy, but there's still a lot of packed sugar in there. You want to balance it with other things, greens and stuff. Okay, so when looking at, let's just talk about the simplest thing. We'll talk about monosaccharides first. So monosaccharides will consist of anywhere between 3 and 8 carbon chains. And it'll have one carbonyl group. So remember, a carbonyl group is a carbon that's double bonded to an oxygen. Depending on where that carbonyl group is, we would call it either an aldose or a ketose. So this over here is got a chain of 1, 2, 3 carbons. Well, 1, 2, 3, and then there's a 4th one down here. We can see that the double bond is at the end though. All right, so I would classify this thing as an aldose. Anything that has an aldehyde is an aldose. Now, if you're starting to get really scared and you're looking at this and going, oh my gosh, do I need to have all these memorized? You don't have to have them memorized. You just need to be able to read their properties. So I could give you something like this and say, hey, is this an aldose or a ketose? You'd have to be able to do that, but I wouldn't expect you to be able to name this thing. Looking at this over here, this is a ketose. Both of these are erythrose. Well, this is erythrose and this is erythrulose. Both have 4 carbons. This one has an aldehyde group, though this has a ketone group. So when naming them, monosaccharides, we like to classify them, not naming them, but when we classify them, we want to determine how many carbons there are. So if there's 3 carbons, we call it triose, 4 is tetrose, 5 is pentose, 6 is hexose. So if I combined that with the previous classification, an aldopentose would be something that has an aldehyde group with 5 carbons. A ketohexose would be something that has 6 carbons with a ketone group on it. So looking at this, this is glyceraldehyde. Again, I'm not going to expect you to know the names here, but I would want you to be able to identify that this is an aldotriose. 1, 2, 3 carbons, and you have an aldehyde at the end. Right here, we've got 4 carbons, aldehyde at the end, aldotetrose, aldopentose, and then this one, which this is fructose, high fructose corn syrup. This is the structure for fructose, but we would classify fructose as a ketohexose. Again, I wouldn't expect you to know this is fructose, but I would want you to know that it's a ketohexose. So go ahead and identify these as aldo or keto, and then as a tetrose, pentose, or hexose. Okay, so for this first one, I can see that there's an aldehyde group, al at the end. So this is an aldo, and it's 1, 2, 3, 4, 5, and 6 carbons. So this one will go with aldohexose. One over here, I have a ketone because it's somewhere in the middle. I need to count up all the carbons. 1, 2, 3, 4, 5. So ketopentose. Any questions on that? It's not too difficult. You just got to be able to identify those. You know, they look scary, and they are scary, but what you need to know about them is not too scary. Okay, so when looking at these things, we need to talk about what is a chirality and what a chiral carbon is. Hold on one second. Oh, it's loading. So when looking at this, like this, it wouldn't be a chiral carbon. This guy would be a chiral carbon. This is 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 not a chiral carbon. What is a chiral carbon? A chiral carbon in its simplest form is that it's connected to 4 different things. Okay. And why is that important? Well, let's talk about chiral molecules. So your left and right hands are examples of chiral objects. It means that there is no way that you can rearrange your left hand and your right hand so that they're identical. Okay, if I take my 2 hands and I turn them palm to you guys, and I try and stack them on top of each other, my thumbs are on the wrong side. Okay. What if I flip one hand so that my thumbs are matching? Well, if I flip my thumbs to match, now the front and backs aren't matching. So there's no possible way to rearrange these in order to get an identical structure. They're unique. Can you use a left-handed glove on a right hand? There's no way to do it. I mean, I've done it before, turned it around backwards, and it doesn't work very well, right? So for a good fit, no. So molecules are structural isomers when they have the same molecular formula, but different bonding arrangements. So look at these two, this thing here, C2H6O. These have, both of these structures here, ethanol and diethyl ether, have this molecular formula, or rather this formula, but they have different structures, right? This looks much different than this. Same thing with this, C3H6O. This is one way we could arrange those atoms. This is another way we could arrange those atoms. Well, stereoisomers will have identical molecular formulas. So we expect them to have the same formulas, but they're not structural and are not structural isomers. Okay, so with atoms bonded in space, with atoms bonded in the same sequence, but in different ways, they are arranged in space. So they're non-superimposable. So this would be a structural isomer in that we have the same formula, but the arrangement is like totally different. A stereoisomer is when the atoms are almost in the same arrangement, but they're just slightly different. And so I can't superimpose them. They're non-superimposable, or they're chiral. So chiral molecules, they have the same number of atoms, but are arranged in a different space. They're non-superimposable. Hands are an example of a chiral. This is it's kind of hard to explain to this over the internet because I can't show you examples in real space, but let's look at some things that are chiral and achiral. So a chiral thing would be these 2 gloves. So the thumb is attached to the lower part of the glove. The fingers are attached to the upper part of the glove, right? The hole is here. That's the same on both of them. So they're relatively ordered in the same structure, but they're not identical. This glove will only fit on your right hand. This glove will only fit on your left hand. So this would be a chiral structure. These shoes would also be a chiral structure, right? The sole is on the bottom. the toe is where the toe is on either one. The laces are on the top, but they don't fit on, you couldn't fit them on the other foot because there are slight adjustments that are unique to them. These structures here, these two bats, we would say that those are achiral. Those I could move or change. Like if I just took this and slid it over here, they would be identical or superimposable. Same thing with these two glasses. If I just took this glass and stuck it in front, it would line up perfectly. There's no way for me to line these two up perfectly. If I flip this one, it's front back. If I slide this one over, it's front, but its thumbs on the wrong side. So how do we get this sort of non-superimposable quality as far as a molecule? Well, molecules are chiral when they have at least one or more chiral carbons. So you need to have a chiral carbon to make the whole molecule chiral. And a carbon atom that's bonded to 4 different groups would be considered a chiral carbon, meaning that it's non-superimposable. So let's look at this thing here. This is a carbon in the center, and it has a hydrogen, a chlorine, an iodine, and a bromine. So I already know that this is a chiral carbon because every one of its partners is different. The mirror image of this thing, right? If I was to flip it over a mirror, so like this would be like the left-handed glove and this would be the right-handed glove. These we would classify as stereoisomers. They're mirror images of each other. There is no way that I can superimpose these on each other and make them identical. Like let's drag, how do they have it? They take this thing and they drag it over here. So let's drag it over here. When I layer them on top of each other, look what happens. The whites match, the blues match, but there's a green and a brown and a green and a brown. Okay, well, what if I rotate this thing by a third? So I keep the white pointing up, but I rotate it. Well, then the green will match with the green, which is great, but the brown will match with the blue, and this blue will match with the brown. So there's no way to rotate this. What if I rotated it up? Then the blue would be off kilter. So we're never getting a situation where I can get all of these 4 partners in exactly the right situation to be identical. So what that means is that these are called enantiomers, or they're different. They have different properties, right? If I could potentially, if I could spin this thing in such a way that it's identical to this, then it would be a bat and a bat, right? But we can't make it a bat and a bat. We have a left glove and a right glove. There's no way to rotate this left glove and make it a right glove. It's never going to happen. So there's no way to rotate this and make it identical to this. Different properties, slightly different properties. This would be an example of an achiral carbon. Okay, so here I've got a carbon in the center and it has 3 different buddies, and then it has a repeat buddy. You guys see how there's 2 bromines here? Well, let's make the mirror image of this. Boop. Okay, put it over here. If I try to superimpose them, all right, well, let's take this and bring it back over here. So we've got these 2 things. They're mirror images of each other. Well, actually, this is saying it's the same thing as this. So they just rotated this 1 rotation, right? They rotated it this way. So the green got moved to here, the brown got moved to here, and the brown got moved to here. So we just rotated it like by a third. Well, look at that. This is the same thing as this. So these guys are identical to each other. So anytime you have a carbon that has 2 buddies that are the same, you will have the same molecules. It's identical. So these would be achiral, or they're not different. So let's look at some of these materials here and decide if they are a chiral or an achiral compound. So this first one here, I need to see if there's any chiral carbons, and I already know that there's a chiral carbon here because they drew it like this. Anytime they have a crisscross like this and they spread out the partners, it means it's chiral, but we'll look at what the partners are. So this carbon right here, he has a hydrogen, he has a chlorine, he has a methyl, and then you need to include the whole tail. Okay, so don't just look at, oh, well, it's connected to, you know, this is connected to a carbon and this is connected to a carbon. No, look at it as a chunk. So we've got an ethyl group here. Those are all different. So we would say this is chiral. Let's look at this one. I've got a carbon. There's a chlorine, a methyl, a hydrogen, and oh, we've got a repeat. That means that this thing is achiral. Or if I was to draw this thing like this instead, C, H, H, Cl, CH3, I could rotate this in such a way that it would just become that. Looking at this one, I've got carbon in the center here. I've got one buddy, 2, 3, 4. All 4 of those are different. All 4 of them have to be different in order to make it chiral. So we would say this thing is chiral, meaning that it can have an enantiomer, or if I arrange them in such a way, I could flip 2 of these and I would have a new structure with slightly different properties. So chiral, achiral, chiral. Now everything, all these things that we were looking at here, back here, these guys, those are known as Fisher projections. So I'm not going to expect you to draw a Fisher projection, but you do need to be able to look at them, read them, determine is it an aldose, a ketose, and if it's, you know, triose, pentose, those. So a Fisher projection is, it's a 2-dimensional representation of what is ideally a 3-dimensional structure, right? These are not just like straight lines. They move forward and back in space because the carbons have 4 bonds. So they're these like little tetrahedral shapes bonded to each other. When drawing a Fisher projection, the most highly oxidized carbon will always be put at the top. It uses vertical lines, so up and down lines, in place of dashes for bonds that go back. So vertical lines mean you're kind of dipping back into the page. Horizontal lines are bonds that are coming forward in space. So when you look at this image right here, this crisscross, there is a carbon sitting right there. And what we would think of as the carbon is kind of in the middle plane. These 2 limbs here are shooting towards your eye. All right, or they're wedged towards you. These vertical lines are the ones that dash back. Those are pointing back into the page. So it's a little tetrahedral, pyramidal, little tetrahedral shape, and these are pointing up, and those are pointing back and down. Okay. So when you see this structure here, this Fisher structure, you will end up seeing that that they don't always put the carbon when it's a chiral carbon. They're just assuming that you know that there's a carbon sitting right there. So if we've got chiral carbons and I rearranged, or I had 2 different things, I have a mirror image of this structure, right? We said that is in fact chiral. It's got 4 different bonds. Well, what if I flipped these 2? And instead of having an OH here, I put the OH on the other side. Well, I didn't do it, but in nature, there's one where the OH is on the other side. These, because they're chiral carbons, I can't superimpose these 2 things. They are actually slightly different. So I need to denote what isomer I'm looking at. And the way that you'll do that is by using in a little prefix of L or D. So how to denote a D or L isomer? Well, you go to the chiral carbon that's farthest down. So the chiral carbon that's farthest away from your top or your carbonyl group. So for this one, it would be this carbon here. Do you guys see how they've written carbon here and they've written carbon here? Like, why did they write carbon there and not carbon there? The carbons that they write in are achiral carbons. The carbons they don't write in are chiral carbons. Okay, so this carbon only has 3 buddies, 1, 2, 3. It doesn't have any chiral qualities. This carbon has this thing, And then it has 2 hydrogens and an OH. So those, that's not a chiral carbon either because it's got 2 hydrogen buddies. So 2 of the same. So you want to go to the lowest or the farthest chiral carbon, which will be the farthest crisscross. If your OH group, so it's based off of the OH group. If your OH group is on the left side, you are an L isomer. Really? Yes, that's what it is. Okay. If your OH group is on the right side, you're going to be a D isomer. So left side L isomer, right side D isomer. Again, do I expect you to look at this thing and know that it's erythrose? No, 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 no. But I would expect you to be able to say, oh, well, this is the L isomer of whatever this thing is, or this is the D isomer of whatever this thing is. And I also would expect you to be able to say, well, there's 1, 2, 3, 4 carbons. So this is a tetrose and it's Al at the end. So it's an aldotetrose. So let's look at these. Indicate whether each pair is a mirror image that cannot be superimposed or whether it's an achiral carbon or something that we can lay on top of each other. Okay, so the first one, these two guys here, these would in fact be mirror images of each other, and they're non-superimposable. So this is a chiral carbon. It's got this thing up here. So this is 1, 2, 3, 4 different things, and this is the mirror image. If I moved this over here, there is no way for me to rotate it in space to get to the same thing. You may be thinking, well, couldn't I just, even if you rotated it this way and brought this to this side, the bromine would be on the top and the CH2OH would be on the bottom. So they're, can't superimpose them. These two are not mirror images. These are achiral carbons. They have 2 things that are the same. So I could rotate, this one in space. Really, if I just rotate it this way, counterclockwise, I will get the same structure. So yes, no. These are 2 different things that have slightly different properties. These are the same thing. All right, looking at these 2, tell me if it's L or D. Okay, so this tells us that both of these are aldose. Al at the end, aldehyde. 1, 2, 3, 4, 5, there's 6 in each of these. So both of them are aldohexose. Just to layer on some more information. L or D? Well, we go down to the lowest chiral carbon, which is this one right here. It's not this one. This is achiral. We go here, look at where the OH is. On this side, it's on the right. Right will give us the D. Left will give us the L. Left L, left L. Remember that. Okay. So I'm gonna pull up. It's actually a good thing for me to check because I want to make sure you have a link to the dry lab for carbohydrates. If it's not on here, I gotta give that to you. Yeah, okay. I'm gonna email it to you. Give me just a second. I'm gonna stop share for just a second. I'm gonna email you guys this carbohydrates lab real quick so that you can have it and you look through it while we're going. I just sent it. It might take a minute. Anyone see it pop up yet? No. You did, Janine got it. Okay, cool. So that should be coming into your inbox pretty soon. So that's the dry lab. We'll look at a little bit of it right now together, and then you can fill in later on if you don't have access to it just yet. Got it. Okay, cool. So we'll kind of, just work on this lab together. It'll be an easy turn in for you all, just so that we can really get the ideas down. Before we move forward, so we're looking at, there's 5 of them. I'll keep the first 4 up here. We're looking at these monosaccharides, and you need to decide whether they're an aldo or a keto, whether they're on top of that, you want to layer that they're a triose, a tetrose, a pentose, or a hexose, and then you want to state whether they're a D or an L isomer. So again, this is like the extent of what I'm going to have you doing with your Fischer structures. I'm not going to say, hey, draw a aldo tetrose D isomer. It's going to be identifying ones that are already written for you. So go ahead and spend a minute looking at these. If you've got the lab up yourself on your own computer, you can fill the information in there. Otherwise, just wait for me. We'll go over it in about 2 minutes. Janine's asking, is there any other lab that isn't posted? Yeah, I believe the amino acids lab I haven't got up there yet. So I'll do that this weekend. I'll give myself a note. I won't waste our time right now doing it. Okay, so let's look at these. This one right here. I want to determine if it's an aldo or a keto. Well, where is my oxygen? Again, remember when it's written as CHO, it's assuming that there's a double bond to the oxygen. Okay, so the double bond is happening right here, al at the end. So this is an aldo. Let's just aldo and keto the rest of these. Here we've got a double bond happening in a central carbon. So this is a keto. Al at the end, this is an aldo. And then this one over here, also an aldo. Now we have to count up the carbons. So one at the crisscross, there's a carbon. So it's 1, 2, 3, 4. 4 would be tetros, aldotetros. Here we've got 1, 2, 3, 4 as well. So this is ketotetros. This one, 1, 2, 3, 4, 5, 6. So this is an aldohexose. This one down here, 1, 2, 3, 4, 5, 6. This is also an aldohexose. So we want to write if it's an L or a D. Go to that last chiral carbon. Here the OH is on the right side, so we're going to say that that's a D dash aldohexose. Here our OH is on the left, so we're going to say that this is an L, ketotetros. These two here are like almost identical to each other, right? They're both aldohexose. The only difference really here is what we can see going on down here. Well, no, both of these. There's another difference in here too. Yeah, so that would give its unique quality. This would be an L aldohexose, and this would also be an L aldohexose, but they're not the same thing because we see a difference here. Again, I wouldn't expect you to know that those are differences in what their names are, but I would want you to know that they're both L aldohexose. Let's look at that last one here. So this has a ketone here in the middle of the chain. So it's keto. There's 1, 2, 3, 4, 5, 6. So this is a ketohexose. And we look at the last chiral carbon, and we see our OH is on the right side. So this would be a D ketohexose. Think you all can handle that? If it's drawn for you? Maybe. Okay. See if there's anything else we can get through on our slides. So this is kind of interesting. A lot of compounds in different biological systems have only one enantiomer that is active. So remember when I said you could have a mirror image and one can't be superimposed on the other one? Well, that can have an effect with enzymes. So if we look here, let's say we've got an enzyme. And the only way that this enzyme is going to work is if this specific molecule, here's our chiral carbon, it has circle, triangle, square. Okay, circle, triangle, square. So circle, triangle, square will fit in like a lock and a key. But this molecule over here has square, triangle, circle. Square, triangle, circle. Oh, it looks so much like this one, right? But it's not quite the same. I try and plug the triangle in, and the circle and the square don't fit. If I rotate it and I try and plug the square in, the triangle and the circle won't fit. Okay, so this is an example of where those things have an effect. A substance used to treat Parkinson's disease is L-DOPA, which is converted to dopamine in the brain where it releases serotonin. The enantiomer of L-dopamine would be D-dopamine. So we have Here's our chiral carbon. Here's the D-dopa, which has a slightly different arrangement, 4 different partners that are just slightly different. This D-dopamine cannot be converted by our brain because it doesn't have this sort of lock and key system working for it. And a lot of drugs, only one of the enantiomers is biologically active. But a lot of drugs have been produced where they mix these enantiomers. A lot of like new drug research is dealing with chiral carbons. Okay, great. So Fisher projections of monosaccharides. Here are 3 monosaccharides that are really important: glucose, galactose, and fructose. Again, I'm not gonna have you draw them, but you do need to know a decent amount about glucose, galactose, and fructose. Both of them, well, this one has the glucose and the galactose both have an aldehyde. The fructose has a ketone. As far as this glucose here, this is D-glucose because we have our OH group on the right. This is D-galactose, and this is D-fructose. All right. In a Fisher projection, the OH group on the chiral carbon farthest from the carbonyl group determines whether it's an L or a D. This is sort of repeat. If we look at ribose, here are 2 enantiomers of ribose. Here's our L because the OH is on the left side. Here's our D because our OH is on the right side. Here's L-glucose. Here's D-glucose. All right, D with the OH being on the right. In this Fisher projection over here of mannose, identify the monosaccharide as either D or L. So again, I wouldn't expect you to know that this is mannose, but I would want you to be able to identify if it's D or L. It's really as simple as boom, boom. We're on the right, so we're gonna say that this is our D isomer. So looking at this structure, I want you to tell me how many chiral carbons are there, or how many chiral centers are there, and then tell me whether it's D or L. Again, I don't expect you to know the names, but I do expect you to be able to read some things off of these. So one easy way to define the chiral carbons, it'll be when it's a Fisher projection, it's the ones with the crisscross. This point here will be chiral. This point here will be chiral. Why isn't this a chiral carbon or a chiral center? Because it only has 1, 2, 3 connections, so not. Why is this not a chiral carbon? Because it has this clunky thing. It has an OH group and it has 2 H's. So if I was to expand it out, it would look like bonded to the OH, bonded to an H, and an H. These 2 things are the same, not a chiral carbon. So we have 2 chiral centers here, or 2 chiral carbons. As far as whether this monosaccharide is D or L, go to the lowest chiral carbon, it's to the left, that makes it L. So let's talk for a minute about glucose before we're gonna go. Glucose, or D-glucose specifically, is found in fruits, corn syrup, and honey. It is an aldohexose, which means that it has an aldehyde and it's 6 carbons strung together. Sometimes we call glucose dextrose. Okay, so this last test, this is for test 5. There are some definition questions on it. All right, so do know these things. Know that dextrose is another name for blood sugar, which is glucose. This is a building block. Glucose is a building block in sucrose, lactose, and maltose, and also in other polysaccharides like cellulose and glycogen, which we'll talk about those multi-saccharide things later. Fructose, D-fructose, can be obtained from sucrose. So It's like sucrose, fructose, glucose. Aren't those all the same thing? No. Glucose is a monosaccharide. Fructose is a monosaccharide. Sucrose is a disaccharide, or it's a combination of two other ones. Fructose is a ketohexose. So whereas glucose is an aldehexose, fructose is a ketohexose. Here's its formula. Look, formulas are the same, okay, but the structure is different. That double bond to the oxygen is at the end here. Here it's in the middle. Fructose is the sweetest of the carbohydrates. It's twice as sweet as sucrose. And then I know we're almost there. Let me just do one more. The sweet taste of honey comes from glucose and fructose. So honey has both glucose and fructose in it. We also have this thing called galactose, specifically D-galactose. So you can see the OH group is on the right. This is an aldehexose as well. So it's 6 carbons chained together with an aldehyde at the end. It's not really found free in nature. It's usually obtained from the disaccharide lactose. So if you're lactose intolerant, things like that, milk, dairy products. It has a similar structure to glucose, except for the OH on carbon 4. So this OH group is flipped. So in a condition called galactosemia, an enzyme needed to convert this galactose into glucose is missing. So you can't break down the galactose. Okay, so we'll stop there. We'll get more into carbohydrates next week. And then we're also gonna do, gosh, I'm spacing. We're gonna do one other chapter. I don't remember what it is. Has to do with DNA and stuff like that. Okay. So, yeah, if you got any questions, stay around. Otherwise, you're good to go. Thanks for pushing forward. Get your test done. Don't worry about carbohydrates for this test, though. That'll be for next week. All right, guys.